Hey everyone, welcome to today's next talk. In today's talk, we are very pleased to have Zirui to give his presentation, Numerical Non-Determinism in Large Model Reasoning and a Systematic Solution to RL Training Inference Mismatch. In today's talk, we are very pleased. And now let me give a brief introduction about today's guest speaker, Professor Zirui Liu. Zirui is an assistant professor from the Department of Computer Science at UMN. He is mostly interested in larger models and their application, focusing on enabling them to combine and process information from diverse sources and domains. And I'm today's host. I'm Da Wei, and I'm currently a second-year PhD student at Arizona State University, and my research focuses on larger model and data mining. And now let's welcome Zirui to give his presentation.
Okay, thank you, David, for the kind introduction. Give me 1 second. Okay, can you guys see my screen?
Yes.
Okay, awesome. Yeah, today I will talk about the numerical issues, or more specifically, non-determinism in the large language model generation and also the train rollout mismatch problem in the reinforcement learning. And actually, the non-determinism is like a feature to the modern computer system. This is a very broad problem that we have in almost every computational system, not only limited to the large language model, but yeah, but recently in the reinforcement learning, it get more and more attentions on these problems. And here's today's talks outline. I will first introduce why we have the non-determinisms in the computation and what are the definitions, why we have them in the uh, large language model and also in the reinforcement learning systems. And secondly, I will talk about what is the impact of numerical non-determinisms on the large language model generation and also RL. And lastly, I will talk about current progress and solutions to this problem. So, uh, like like David mentioned, so today's talk is mainly focused on the system perspective, not the algorithm perspective. Okay, so let's start with the IEEE 754 data format. So actually, because our computers, we use binary representations. That means uh, every every flow number, we only have limited precision. And one commonly used data format is called the IEEE 754. So here I put one example of floating point 32, or in short, LP32, LP16, and BF16. These three most commonly used data format in the deep learning. So usually speaking, for the IEEE 754, we have three parts. The first part is the sign bit, which tell a computer whether this number is positive number or negative number. And second, we have the exponent bit, and exponent bit control the numerical range. So if you have more exponent bit, you can represent like larger numbers. And also we have the mantissa bits. Mantissa bits actually control the precision. So that means it's like the resolution of your numbers. So if you have more mantissa bit, actually you can represent a floating point number in a more accurate way. So yeah, currently the most commonly used one is this one, the BF16. So usually speaking, most all uh, model you download from Hugging Face, they are using B float 16 in default. And just like I mentioned, so because of every floating number, they only got limited precision. So that means you have something called the truncation error. So for example, if you add two number together, so for example, A plus B, so because they only have limited precision. So that means you calculate the intermediate results of A plus B, and then you must rounding it off to the numerical representation. So here, so that means if you do the floating point uh, operations or arithmetic in different order, you actually will get slightly different results. So here I show two intuitive examples. So for example, A, B, C equals 0.1, negative 0.1, and 0.2. So if you do, for example, if you first summarize A plus B, then plus C, the results is different to like you first calculate A plus C, then plus B, because you got because every because after every intermediate results, you have one rounding step, and if you have the rounding step, you have the rounding errors. So that means floating point arithmetic is often not associative, although it is very close to associative, but um, it's not associative. So just like I mentioned at the beginning of the talk, this problem is very fundamental and actually apply to all kinds of computation if you use uh, the IEEE 754. So yeah, this problem is not only limited to deep learning, actually. And so because of this issue, let me be clear. So if you can control your entire workflow followed exactly the same floating point arithmetic order, you can actually get the identical or bitwise identical results. But in practice, there are many different factors that affect your floating point operation orders. So here I just name a few. Actually, there are many more factors other than these three. So for example, the first one is that uh, nowadays we are using GPU to do the deep learning workload, right? So that means many GPU threads, they are running parallelly, and you cannot predict which one will finish. So they will finish unpredictably. And there are some operation like atomic add. Atomic add means, so for example, you have, let's say, multiple GPU threads, and they write to the same address simultaneously. So although they have a mechanism to resolve the confliction. So, but you can see the problem is that you cannot predict which thread first write to this address. So you have non-deterministic if you use atomic add. This and by the way, atomic add is often used in the split key matrix multiplication, these CUDA kernels. And also, actually, GPU kernel, they also got their own hyperparameters, right? So for example, if you use GIM, you actually have different block size for the same kernel. So this is actually what happens under the hood. So it's uh, like PyTorch, they have some code to route your input to different kernels according to your input size. So for example, if your input size is small, they will route to a highly optimized GPU kernel tailored for doing small size matrix multiplication, something like that. So that means if you change the input size, they often route to different GPU kernels. And if the kernel is different, definitely usually speaking, the final floating point arithmetic order is different. And also the hardware and the software difference. Okay, so uh, so for example, the currently arguably one of the most commonly used GPU architecture is Hopper, like H100 or H800, and on these, so for example, there are many hardware primitives only available for Hopper GPUs. Not and also their operations is not. Oh, sorry, this primitive is not available on other GPU architecture like some, for example, Blackwell or or Tesla, something like that. And that's the reason why that's the reason why, usually speaking, when you change the GPU architecture, you need to write a new version of the kernel. if you want to squeeze out every thread out of your GPUs. So that means, usually speaking, if the hardware is different, the kernel will also be implemented differently to maximize the throughput. And if the like I said, if the kernel is different, the accumulation order also change a lot. And there are many existing efforts to this problem. So like I mentioned, this is a very old problem, right? So ideally, if you want to solve the problem, you need to eliminate or try to minimize the rounding errors. So if you want to minimize the rounding errors, one way is to use higher precision. For example, if you use double precision, uh, then the rounding error is much smaller compared to 32-bit or 16-bit, right? And this is also the reason why double precision is widely used in the traditional scientific computing. And also you can, uh, like I mentioned, the problem is that uh, the floating point arithmetic is not associative. So you can try to another way is that you can try to reduce the accumulation error. So for example, there are some algorithm called Kahan summation and exact dot product accumulator. So actually, in the modern like gem kernel, so usually speaking, the accumulator they will use higher precision. Like for example, although for the large language model, majority of the model weights is stored in 16-bit, but actually when they do gem, the internal accumulator is in 32-bit. In this way, they try to reduce the rounding error. Oh, by the way, these features are already available in the current software stack, and also there are also some efforts from the hardware side, like CUDA FMA. FMA is short for fuse, manipulate, and add. So that means they just do one rounding step for x times y plus z instead of normally two rounding step. In this way, they can reduce the rounding errors. Uh, but although with all these efforts, we still frequently notice that large language model generation is not deterministic. So intuitively, this problem is getting worse when you output a long trajectory. So the intuition is very simple. So uh, for example, if you only generate one token, uh, then you just have one step rounding error. But if you generate 1,000 token, then you have 1,000 step rounding errors. So the rounding error, they will accumulate it step by step and finally lead to a completely different results. So here to get a sense, here I show a illustration of the uh, DeepSeek reasoning model. You can see if you use 16-bit and if you just even if you use the greedy decoding or zero temperature control the random seed just by changing uh, the evaluation batch size, you can get a completely different results. So actually, like I mentioned, this problem is not new, but it is not that severe for the traditional machine learning model like convolutional neural network. Because when you use convolutional neural network, usually speaking, you just output a class label, and this is like a one-step generation. But for large language model, especially for the reasoning model, you are generating thousands or hundreds of thousands of tokens. So every step you have a small rounding error. They will accumulate it in your KV cache. And when the sequence trajectory is long, then yeah, you cannot control it. You cannot control it. So this is the root cause of the non-determinism in the large language model. So uh, usually speaking, if you change your evaluation batch size, change your GPU count, or change your GPU version, they will also change your final model results. And this also related to another very popular problem in the reinforcement learning infrastructure. This problem is called training and rollout mismatch. So here is a little bit background regarding reinforcement learning is that in reinforcement learning, uh, if you do on-policy learning, you need to first use this model to roll out some of their own experiments or trajectories, and then you train the model on your sampled trajectory. And if you use PPO or GRPO, you need to have a importance ratio. The ratio is the current model's probability to the token probability from the old models. So that means you the same token you need to calculate its probability in the inference engine and also in the training engine in order to use the importance sampling. So here the problem is that just like I mentioned, it is even impossible to get beat for beat identical results between training and the inference engine if two identical inference runs don't match. So that means if you two inference run cannot match, then definitely you cannot match the training run and the inference run. So here's the problem. And there are many existing efforts on this domain. I will talk about it later. But here I want to give you a uh, quick analysis why this is hard. Okay, so rollout is basically inference. So for large language model inference, uh, you have prefill and decode and plus KV cache. Sorry, this is a typo. It is prefill, decode, and also you have KV cache. But for training, you only have the prefill. And so that means you have a two-stage rollout phase and one-stage training phase. And in the decoding phase, that you can will the bench size is equals one. Oh, sorry, it's not like bench size equals one. It's like the uh for each trajectory you only have one token in the decoding. It's not like in the prefill or training, you all of the tokens they are uh in the sequence. So usually speaking, in the inference stage, all all of the token in the batch they will be flattened into a super long trajectory. So that means the batch size they will misaligned. And also the training and the rollout engine they will definitely employ different parallel strategy, right? So for example, if you use VLLM or SLM, if you are operating on a dense model, you often use tensor parallel between the GPU within the same node and use pipeline parallel uh, among different servers. And the training on the other side, usually speaking, we often use fully sharded data parallel. So you say we shard the model differently, and definitely on each GPU we have different workload. And just like I mentioned, different workload they will route to different kernel, and then they behave differently. And also in different engine, they will implement the same operation differently for squeeze out the GPU performance. So for example, we have the rotary precision embedding, right? In the training system, we have the rope. In the inference system, also got the rope. And these two rope, usually speaking, they are inferred differently in like say VLLM or deep speed uh, zero systems. So if you want to align training and raw, actually it is a huge engineering effort. And why this problem come to the why this problem is getting more and more popular is because nowadays the leading model they are mixed of expert, and and this problem is very severe on the mixed of expert. The insight is very simple. So the mix of expert they will route different tokens to the corresponding expert, right? So the router itself is a discrete process. So the numerical precision issue, they will lead to a problem that the same token, they may lead to different expert in two different runs. So that means, for example, in the training system, the token they will probably route to the expert 1 and 3, but in the inference system, they will route to the expert 1 and 2. Then you can expect in this case, the final result is very or even completely different. So here I attached one running log from the VLLM deterministic mode. So here you can see the orange line is the original MOE RL, and the black line is uh, the one with deterministic mod. So you can see the without the deterministic kernels, the original IL run, they have suboptimal reward compared to the one with correct infrastructure support. And yeah, that's the reason why this problem is very popular and very severe to the midst of expert. So like I mentioned, this problem is very popular. So there are many existing efforts. So for example, the GSP, there are many efforts on, for example, developing the numerical stable reinforcement learning algorithm like GSPO, SAPO, router replay, and also people they also suggest using the FP16 precision in the reinforcement learning. So if you still remember the first figure I displayed between the FP16 and the BF16, the difference between them is that FP16, they got more mantissa bit. So that means they have better precision compared to the BF16. So you can expect in this case, the accumulation error is smaller for XP16. And also there are another line of work is to correct the importance sampling ratio, like TIS at the token level importance sampling. And they do a they redo another step of importance sampling to correct the misaligned one. So in my opinion, these two line of work, they are all algorithm level fakes. So they are lightweight, easy to try and implement, and also they got minimal overhead. This is their advantage. But the disadvantage of them is that, uh, because you adjust the algorithm, so that means they coupled with the algorithm design. So in this case, it's very hard to say after applying this design, the performance gain is because you're designing a more stable algorithm or uh, some other effects from your modification that lead to better performance. And also another thing is that this problem, so in my opinion, algorithm level fix, they cannot solve the problem fundamentally. By fundamentally, I mean you just eliminated the gap. So the gap is numerically 0. So they cannot do that because they are algorithm level fix, right? So like you try to reduce the error, but not solve it. And another on the other side, there are the same system level solutions. And this is also the focus of this talk. Like for example, the deterministic mod in the VLLM or SGLang. So the advantage of them is that they solve the problem fundamentally. So you can actually prove that the gap is 0, guaranteed. But the disadvantage of them is that they are very heavy. And just like I mentioned, is lots of engineering efforts. And also because if you want to achieve 0 gap, you need to enforce the training and the rollout engine to use the same set of kernel. So that means you have a much larger overhead compared to the algorithm level fix. I will stop here a little bit just in case you guys have any questions regarding the background of large language model generation and the training rollout mismatch.
Yeah, I think it's very clear, and so far we don't have any questions, so maybe it's really good to continue.
Okay, good. And yeah, now we move to the impact of the numerical non-determinism on the large language model evaluation. So, there are since the release of DeepSeek R1, there are tons of papers on the reasoning, right? So, for example, the many many people they try to improve the reasoning mathematical reasoning performance of the DeepSeek model and also develop their own new algorithm. And if you want to get your paper accepted, so you need to compare your paper with other algorithm, right? So here come to the tricky part. So uh, let me first introduce the background on the commonly used evaluation uh, protocol. So there are two commonly used method. The first one is greedy decoding. That means you choose the token with highest probability, and the other one is random sampling. So for example, we set the hyperparameter top p and top k. And usually speaking, for the when people use greedy decoding, we just do the generation once. So because ideally it should be deterministic, right? So we run the experiment once and get the final results and report it. And for the random sampling, we run it with multiple trials and average the final results. So and also usually speaking, for the greedy decoding, we just report a single run accuracy, and for the random sampling, we report the average accuracy or the pass at k. And here our experimental setting set, which we change the number of GPUs, GPU version, and also the batch size. And change just like we analyzed, changing these factors, they will impact the micro level token scheduler and the underlying kernel selections and the implementations, and thus changing the floating point arithmetic orders. And we are using the VLLM 0.8.2 to conduct our evaluation. So long story short is that we found for reasoning model, changing this system config, they will lead to completely different answer actually. So here, this figure, I show the output length after changing these factors with different numerical position. So you can see for the non-reasoning model, the final output length is not the variance is not that large. But for the reasoning model, because they are generating lots of tokens and the error accumulation, their output length varies significantly. And you can see they are often around 5,000, 2,000 to 5,000 in terms of the output length. So I know there are many people they are doing long to short evaluation. So if you do long to short evaluation, you should not use greedy decoding or not just run it once and report the final run. And also, greedy decoding is not recommended also from the accuracy perspective. So for example, for the smaller data set like AIME, for if I remember correctly, AIME they only got 30-ish questions. So that means this is a fairly small data set. So for smaller data set, if you have the system config difference, so the final results difference is very large. So we show that actually just by changing the GPU types, GPU or the TP size and your GPU type, you can have a like 10% accurate variance. So that means like let's say you just change your batch size from 6 to 10, and then the accuracy boost 10% when you use greedy decoding for the long reasoning model. So this is very bad uh, if you want to demonstrate your algorithm is better. And here we come to the random sampling. So random sampling, you can see is much better. So because we run experiment with multiple trials and report the average accuracy, so it's much better. So here uh, we you see we run the different we run each question with different number of trials. So for example, here for the math 500, we run each question with 4 trials. So that means for each questions, we generate 4 different answers, and the accuracy amount is 4 answers. And similarly for the AME, we do 2 separate uh, configurations. So you can see for smaller data set, you need to run it with more trials. Like for AME, I highly recommend run it with at least 16 trials. Anything less than 16 trials, you will definitely have much higher variance. So for example, the range is at 0.3 to 2% accuracy. So why I think this is very important is because uh, so if you have 2% variance purely from hardware or system configuration, that means uh, you need to 4% or 6% accuracy improvement in order to demonstrate your improvement is significant. So this is the p-value or this is what we call the statistical significance. So if your error follows Gaussian distribution, you need to have two sigma to demonstrate you have 95% chance that your model is better than the baseline, and 3 sigma to demonstrate your model is 99% uh, confidence that better than the baseline. So that means if you have 2% variance, you need to have at least 4% accuracy improvement compared to the baseline in order to demonstrate that your improvement is significant. But if you think about the reasoning papers you see it during the last year, how many of them they report the error bar, or did they do, for example, 16 random trials or 16 random trials or 64 random trials? And in my opinion, if so, uh, for the reasoning model, we are optimizing the path at k, right? So ideally, we should really report the error bar, and in order to demonstrate one algorithm is better, we should, let's say, demonstrate in my opinion, at least 2 sigma. So any improvement within 1 sigma is not significant. And this is and here the sigma 2% is purely from the hardware. It's not like from the algorithm. So algorithm they got, so for example, the model itself got another sigma. So they are complicating each other. But here I just want to show you guys why this is important. So because uh, if we want to measure the progress, we need to uh, report the number scientific, very rigorous and scientific. Oh, and also in a reproducible way. And here I also want to show some insights and other insights why reasoning model they are so sensitive to the numerical errors. So like I mentioned, this is a very old problem, right? And why reasoning model this problem is very severe. Previously I gave one explanation that uh, reasoning reasoning model they generate more tokens and then the error get accumulate. Here I also show another reason why this is very severe from the distribution perspective. So let's do a thought experiment. In what case the model is not affected by the numerical error at all, even if you generate very long token, very long trajectories. It's one hot distribution. So suppose for every position, for every token to be generated, your model's distribution is one hot. Then no matter how large, then usually speaking, for this distribution, it is very robust to the numerical error. So the insight is very simple. There are still numerical error, right? So numerical error is expected to be small. So if you have one hot distribution, even though they will slightly change the order of different tokens, they should not affect the final token sampled significantly, right? So it is much more robust to the uniform distribution. And here's another example. On the other side, this is the distribution that is the most vulnerable to the numerical error. It's uniform distribution. So imagine if you have a uniform distribution, uh, that means a small rounding error, then will change the ranking of different tokens significantly. And unfortunately, for the current, no matter you are using greedy decoding or top key or the top key or top key sampling, they are they are sensitive to the ranking measure. Because so for example, greedy decoding, you are picking the rank one token, right? And also in the top K and top P token, you need to eliminate uh, tokens according to the token ranking. So if the token ranking changes, you actually will exclude or include more different set of tokens. So unfortunately or fortunately, reasoning model they are more close to the uniform distribution. And we show one quick example for DeepSeek detailed model. So here you see the top two tokens often have a on par probability. So the gap between them is very small. So you see in this case, if I change the hardware configuration, then the token ranking they will just flipped, and like 60% in the probability is nothing in the for the under the BF16. And you can see the token probability gap is very small. And, and here, another insight why this happens. Because in the reinforcement learning, if we want to have good performance, we need to have we need to explore different reasoning trajectory, right? So that means we have some high entropy tokens. So that means there are some at some position the token they have uh, the distribution have much higher entropy. So in this way, the model can explore different reasoning paths. So in my opinion, this is more like a feature, not a bug to the reasoning model. So in the reasoning model, if we do reinforcement learning, we actually make the model to have higher entropy token. And higher entropy token is more sensitive to the numerical errors by design. So yeah, this is a problem. So now we come to the solution part. Like I showed, we in our benchmark paper, we show bench size, evaluation bench size, TP size, and GPU version. They will affect the final results. And fortunate thing is that for the first two problem, we have the deterministic kernels. And in my opinion, aligning different results among different GPU versions is very hard because just like I analyzed, different GPU architecture that have different hardware primitives, and if they are using different hardware primitives, it is, in my opinion, very hard to align them to have the same results. Probably you need to enforce them to use the same hardware primitives. So for example, all of them, they are using CUDA core instead of Tensor core, but this is not realistic in my opinion. Okay, the first very famous one is batch invariant kernel, released by the Thinking Machine Lab, and this one is already available in the VLLM and SG-Long. And long story short is that their key idea is they try to parallel the computation along the batch size dimension. So in this way, they can ensure that no matter what is the batch size, you still have the same results. And in order to do this, they build the batch invariant RMS norm, batch invariant matmul, and batch invariant attention. And by fixing the reduction strategy, they can uh, output remain identical regardless of the batch size or the server load. And if you recall, uh, the challenge between in IO for aligning training and rollout. One problem is that rollout they have the training and rollout they have the training and decode. Sorry, rollout they have the prefill and the decode. On the other side, training they only got the so-called prefill. And if we can do the batch environment kernel, so that means we can align these two. Uh, we can align the prefill and the decode, and also we can align the results when we use the continuous batching. This is one widely used web optimization for the online serving. Okay, here is one. Here is one illustration. You just want to make sure the kernel they do the computation in a data parallel way. So you split the workload among the batch dimension. You want our kernels strictly follow this rule. So in this way, they don't entangle with each other. And finally got the batch invariant results. And another harder invariant kernel is called TP invariant kernel. So that means uh, no matter what is the TP size, you got identical results. Why I say this is harder is because uh, in the serving system, the TP they actually follow a split key implementation. So split key means for the matrix multiplication between two matrices, they split the workload among the inner or the shared k dimension, and then followed by our radius. This is the split k mathematical. Why this is hard is because if you want to align the results between one GPU and four GPU, that means you want to align the all radius and also the mathematical. So this is very hard. And we in our lab we developed the TP environment kernel. So I want to skip the engineering details, but only the design principle. Our key idea is that we want to enforce all reduce and also the GPU matrix multiplication kernel. They follow the same binary tree reduce order. In this way, we can make sure the final, no matter what is the GPU size you use, that you still got the same final result. So for example, red one is our kernel. So uh, the blue the blue one the blue one indicates calculate within each GPU. So for example, you can see four GPU and two GPU they follow the same tree structure, and in this way, the final results or the final accumulation order is still the same. So this is our key idea. Uh, yeah, we implemented the binary. We implemented the binary tree based MATML and Aurelius. And the good thing is that if we have the batch invariant kernel and TP invariant kernel, we can actually uh, make sure your reinforcement learning to have the zero probability gap. So no, so I want to be clear. In this setting, we are using multiple GPU for the VLLM and multiple GPU for the FSDP. If you only use batch environment kernel, you can ensure zero probability gap only using one GPU. But if you use multiple GPU because of the all radius and the TP mismatch problem I mentioned, you cannot have the same results. So in this case, you can use our further use our TP environment kernel to ensure a guaranteed zero probability gap. And like I mentioned, there is no free lunch. So you get the identical results, but you pay kernel inefficiency because like I you also you add the extra structure to your GPU kernel, so they cannot leverage the most efficient implementation. So this is the tax you must pay for the system efforts. Okay, so in summary, numerical stability is a long-standing problem in the machine learning. And why are reasoning model much more sensitive? is because the high entropy of the minority tokens and also the error accumulations, and also what factors impact the results and introduce actual variance, GPU version, GPU counts, or the TP size, or your GPU, how many GPU you are using, and also the evaluation bench size. Finally, what are the potential solutions? You can use algorithm level fix like token level importance sampling using GSPO, using router replay for your MOE model using FP16 precisions. On the other side, you can also use the deterministic model, deterministic kernels introduced in this talk. And in my opinion, in the future, if we want to solve the problem, we need to combine the algorithm and the system efforts. In my opinion, uh, uh, in my opinion, we need to combine the best thing of the both world because in the future we want to do more efficient reinforcement learning system. So that means we need to further lower the numerical precision. Like we want to do LP8 IL, LP6 or LP6, LP4 IL. And in that case, pure algorithm level fix may fail, and also uh, pure system efforts may have much higher system overhead. So better to combine both of them. That's it. Uh, yeah, I'm happy to answer any questions.
Yeah, first, thanks to Ray for this very impressive talk. And to me, one thing I learned is like for a large language model, especially for those reasoning model, when we propose some new method, maybe we should be very careful, right? Especially when we do those reasoning tasks, we need maybe do multiple experiments before we claim our method to be effective. And here we also collect some questions from our audience, and also you are very welcome to share any question or comment in different platforms. So the first question is, because we mentioned that in the large language model, especially in reasoning model, the non-determinism is very significant. Like it will lead to a very large variance in both length and accuracy. So
Mm,
the question is, does that mean nowadays research papers experiment for reinforcement learning or for reasoning tasks
mm.
is not reliable, or how can we trust it?
Uh, Good questions. So usually speaking, when I read the reasoning paper, I will check whether they report their experiment setting. So in my opinion, uh, greedy decoding results is not that reliable. So I already told you the reason. So and I think the best or one strategy should be adopted by the community is that, like I mentioned, run experiment with multiple trials. I think DeepSeek they really do the great job. So if you check the DeepSeek paper for every reasoning task, they run. Sorry, I cannot remember that exactly, but if I remember correctly, it's 64 trials per questions, 64. And if you think the experiment time is too long, maybe you can cut it to like 32 or 16. But in my opinion, not great decoding. And also, it should better to report the error bar. And this is very important. Just like I mentioned, any improvement within one standard deviation is not significant from the statistic perspective. Uh, yeah, ideally, we should have two sigma improvement.
Yes, yes, I think that's very insightful. Yeah, basically we just need to be more careful and focus more on their experiment setting, for example, the decoding method and the error bar, right? And here is another question, like how much system overhead do these new kernels introduce?
Oh, very good questions. Let me get back to you can see this is a VLLM official report. So you see the overhead is, in my opinion, is huge. So you see without deterministic is 38 minutes, and using this method is 1.5 hours. So more than twice. more than 100% overhead.
Yeah, I see. Yeah, that might be the trade-off we need to pay to make it
Yeah,
more determinism.
yeah.
Yeah, and here,
Sorry, I want
yeah,
to have one more word because I work on infrastructure. I know engineering problem they can improve exponentially. So that means, for example, for this year it's 100%, maybe next year it's like 10%. So because engineering, in my opinion, many infrastructure, so currently the kernel is still highly unoptimized, and I'm pretty optimistic that if we LLM team they put enough resource on this problem, they should they should at least cut it. So
yeah,
I cannot give a concrete number, but in my opinion, they can cut it significantly.
yeah, and it also means there is a lot of room in that area to be improved, right? So if you're
Yeah,
interested in this problem, maybe just give it a try.
yeah,
Yeah,
yeah.
yeah, thanks for the answering. And another question is there a specific module in the model that introduced most of the numerical instability? For example, softmax sensitivity, attention accumulation, or others?
Great questions. I didn't do this ablation study, so I don't know. But my education guess is that probably it's the KV cache and attention because KV cache they will uh they will just so KV cache is like they just accumulated, and everything other is like, for example, MLP layer, you pass through it and then you throw away the results. They are not accumulated. So probably KV cache, but I don't do the ablation study.
Yeah, that makes sense. And let me see. Yeah, I didn't find any more questions, but here's the questions
Mm,
for me from me. So
mm.
basically, you mentioned we have like two levels of method. The first level is algorithm level,
Yeah,
like GSPO,
yeah,
and the second level is system level or computing level,
mm,
which you focus on in the two papers.
yeah,
But actually, I'm also very interested in this algorithm level,
mm,
and uh, maybe I'm not correct, but from my perspective, those algorithm level methods, they are not designed specifically for this non-determinism, but
mm,
they have some advantage.
yeah, yeah.
So can we, for example, design some algorithm that could work for reducing this non-determinism? For example, we just using a RL to give it a reward if we, for example, we sample it multiple times and it gives very consistent answer or consistent result.
Very good questions. I think, yeah, you're raising a very good point. I think the most fixed solution to your mentioned is GSPO. So GSPO, they are like they instead of do the token level, they do the sequence level. So sequence level is much stable compared to the token level, right? But also sequence level, they may have other, for example, benefits to this problem, right? So for in the method mentioned in this slide, for example, the router replay is specific to this problem for the MOE model. And it's very useful in my opinion. Router replay is probably one must have for defeating this problem. So that means you record the export choice for each token in the rollout engine, and you replay it in the training engine. Instead of in the training engine, you redo the token selection. This is router replay, and also this one is also very useful. And in my opinion, for most cases, if you use router replay plus token level importance sampling, it will improve the stability significantly. But just like that way you mentioned, uh, yeah, there are many algorithms not only improve the stability but also like improve the performance. And I think GSPO probably is one example.
I see. Yeah, maybe later I will take a close look at this rotor replay paper. And
Yeah.
we have one more question from our audience. The question is, could you explain why MOE model is more sensitive to numerical error?
Oh,
And yeah,
yeah.
if so, can we take router more robust? That,
Uh,
yeah,
yeah. Go ahead. Sorry.
yeah, I mean, the audience wonder if that sensitivity is based on or from the router. Yeah.
Yeah, I think the audience understanding is correct. It's from the router. Um, Here is one intuition why MOE is more uh sensitive to MOE. So, sorry, it's more sensitive to rounding errors. Um, in the MOE, for each token, you need to select a top K aspert, right? So this top K aspert is from one linear layer and following by a softmax. And in practice, you often got on par expert. By on par expert, I mean, so for example, okay, let's do a thought experiment. Okay, so imagine one token, their expert pro probability is like uh 65.1 and 60 sorry 45.1 and 45. Their their numerical difference is only 0.1%. So in this case, in different engine, they will flip the top aspect order. And in this case, they may route to different aspect. So this happened because in MOE model, you often got on par aspect, just like why greedy decoding is not that stable. In greedy decoding, you got on par tokens in the final selection. But in the MOE, you often got on par aspect for for different tokens. And in this case, small rounding error, they will trigger different aspert orders. And yes, we can develop more robust routers. Uh, like we can explicitly enlarge the probability gap between different aspects. Actually, we can do that. We can just add one regularizer to do that. Uh, but in my opinion, for at least for MOE-IO, router replay is a better solution in my opinion. So we actually get rid of this problem, right? So we just run it once and record it and reuse it in the training. So yeah, and
Yeah.
yeah, it's much
Yeah.
easier in my opinion.
Yeah, I think that's very interesting, especially nowadays we have very sparse MOE model. I think that would make the problem even worse. And here we have a new question. So basically, the question is, we know min-max in their model introduce
Mm,
CISPO,
mm,
CISPO.
mm, mm,
And instead of important sampling, they are using policy gradient.
mm, mm,
So what about this one's numerical stability? I think it's about a
mm.
specific algorithm.
Sorry, I'm not familiar with the mentioned algorithm. Sorry, what's the name again? Just
It's
say.
CISPO.
Sorry, yeah. Sorry, I'm not familiar with CISPO, but I think in general, PPO family they have this problem because they have the important sampling. So let me think. Oh, sorry. After a second thought, I think yeah. After a second thought, if we have on policy IL, we have this problem because we must the training engine still need to use the same probability to the token. Sorry, the training engine still need to use the same probability distribution uh, given by the sampling distribution. But to be honest, I don't know whether policy gradient is more robust to numerical error or not. So, but my guess is if Minimax they use this algorithm in their paper or in their production, it should be better than PPO. This is my education guess.
Yes, that makes sense. And due to the time limitation, let's have the last question. So the question is, with router replay, MOE is more like denser model?
Oh, no, no, no. It's different thing. Router replay just means you record, let's say, okay, let's say uh, you have an MOE model, you run a inference pass, or you run the rollout pass, and you record which aspect the every token router to. You record it. For example, you can imagine it dump it to a JSON, and when you rerun the experiment, you just unload this JSON file, and you don't do any routing at all. You just follow exactly the how token is routed in the first run to the second run. Basically, like copy the routing path to the second run. In this way, you you eliminate um the routing issue. And after applying router replay, if you mean more similar to dense model, if by more similar to dense model, if you mean uh they are we reduce the sensitivity level to the dense model from the MOE model to the dense level. I think the answer is yes. So after applying the router replay, we reduce the sensitivity of the MOE model down to the dense model level.
Yes, so basically we don't need to let the router to calculate in the second time, right? We just
Yeah, yeah.
record it in the first time. So we just reduce the non-determinism in router level.
Yeah, yeah, yeah. Correct, correct, correct.
I see, yeah. All right, let's ask again for Zuri's very impressive talk. And I think that's it for today's talk.